Then the second one that I spent much time over the years is how to help the students learn to approach problem solving in a systematic way. I am going to discuss this in the context of a course on heat and mass transfer, but the idea is very generally applicable. In fact, I have tested that with other subject matter. What was the problem here? In a heat transfer course, for example, we come and provide these formulas one after the other as we go from, let's say, steady state formula like this one to unsteady state formula and so on. So we go in some order, and then we come and ask this question in the exam that says estimate the heat generation in a whale. So the eternal question is which formula to use. This is not an easy topic as the student is learning problem solving. It is not obvious to the student at all. Existing guidelines are of course there for problem solving. Like this one here from a physics book, here we have these steps: identify, set up, execute, evaluate. These steps are there, but they do not really address one of the very critical steps, which is the one I just mentioned, which is which formula to use. The way we have this identify, set up, execute, and evaluate, it pretty much assumes that the student knows the formula to use. Somewhere between identifying and setting up is the difficulty that the students typically have. So what I did was I divided the problem solving into 4 parts, not unlike the solved problem I just showed 2 slides ago, but further broke down each step into these generic questions. For example, defining the problem, we have what are we solving for? What is the schematic? What are the assumptions given? So it is this second step of problem solving that I want to draw your attention to, that is the generating and selecting alternative solutions. That was the critical step I said was missing in the example I showed 2 slides ago. So in this second step, they ask questions like how many ways to solve this type and what type is easiest. For this, they need another piece of information that I will show you in the next slide. For now, you see the steps and each one broken down into more generic questions. I also automated this. This means I implemented them on a learning management platform, in this case edX. So in that one, I have questions first to prime their thinking. Then I have video that actually goes through the steps where I solve it for them. And then I have quiz again that tests their learning. All of these are automated and scalable because they're done in the learning management software. And so these are some of the details here. This is now the other critical part of the process. It is to generate the meta-knowledge that relates all the different solutions. Once the solution tree is generated, like this one, for example, steady state, unsteady state, and so on. Once this tree is generated, it is easy to traverse this tree for a given problem. This traversing is what an expert does. Perhaps without even thinking, but here we are unpacking the expert's knowledge. So this is the other critical part. This part, together with what I showed in the previous slide, is the tool that we have developed to help the student develop problem-solving abilities. Did it work? So I want to share with you very indirect measures of whether it worked or how much it worked. So first part is I want to show how this web-based approach to learning problem solving, how much did they like it in relation to a live problem solving session. So I want to say that these different features of a web-based software, like it can be used anytime, anywhere, or it can have personalized feedback, or it allows them to review later, or this step-by-step walking through that is done very well in such a software. These features are liked very uniformly by the students. The features that they didn't care for as much are also the features that are not well done in this kind of web-based approach. For example, group setting, that we are not able to do in the web-based approach, but they did not seem to care about that anyway. So again, we have another some data on students' self-assessment of problem-solving ability. And so what you see here is that over 80% felt that it improved their problem-solving ability in heat and mass transfer. But the next one is even more interesting, that we asked the generic question, do they feel that because of this process they feel they are better problem solver in general, not just in heat and mass transfer, but in general. And again, the students' self-assessment says they felt 80% or more felt that yes, they are better problem solver. So they probably worked at least to some extent. What does all this mean? It means we provide an approach to teaching problem solving that is generic, instructor-friendly, and scalable. And it is using active learning concepts in an online platform.